Okay folks, welcome to this Concepts Explainer where we're going to look at thermistors and LDRs. This is a response to one of my students who told me that they thought that they found the ideas about thermistors and LDRs quite tricky and needed a bit of a recap. If you've got any other topics that you'd like to recap, please let me know and I'm happy to put something together for you. We're going to look at some general ideas about thermistors and LDRs and then look at specific past paper question. And I think that should probably do us for this topic. So let's go for it. Let's start with thermistors. A thermistor, the name comes from thermal resistor. It's a resistor whose behavior depends on its temperature. Okay, now you can see here the symbol for the thermistor. The thermistor is that common resistor rectangle, but with a line through it, specifically a line and not an arrow. And that line, if we look at it from left to right, is flat, and then it kind of goes up into a diagonal line. And that, to me, looks like the temperature time graph from when we heat substances through their melting point, etc. Okay, that's the way I would remember this as well. You may have your own way of doing so as well. If we look at the graph that's on the screen, we can see the resistance will go down as the temperature goes up. Now this is opposite to our wires. Okay, a thermistor behaves in a different way to our wires. In the case of a wire, the resistance actually goes up if you're studying that at AS level, whereas with a thermistor, the resistance goes down with temperature. If you notice here on the right-hand side, we've got a very similar graph for a light-dependent resistor. As the light intensity or brightness goes up, the resistance will go down. And another similarity is that we have got our little box there. Okay, that's the resistor again. And the arrows going in, that's the light. So this is the light-dependent resistor. You notice that they are basically the same thing, the thermistor and the LDR. Just one of them works with temperature and the other one works with light intensity. So in the following question, we could easily substitute light intensity for temperature, okay, or an LDR through a thermistor. But we're going to look very quickly at this past paper question, which is about thermistors in particular. Here we go, we've got a thermistor there connected in series with a battery and with an ammeter. And we're heating the thermistor and measuring the current. Notice we're measuring the current and not the resistance. So it's probably a slightly surprising graph for you. You can see here that we're going up. Well, that means we're looking at the current in this thing. The first thing we're asked to do is to state the current passing through the thermistor at a certain temperature. We're looking at 47 degrees. Okay, so that's 4 boxes along from 45. Okay, and I can see that that cuts the graph at our point, which is around about 0.130. Okay, I'm going. We've got to be a bit careful with our scale because one big box is going to be 0.05, and we're going 6 small boxes up there, and so they're therefore 0.13. Okay, so it's just simply a case of getting your ruler out and copying out the graph, or reading off the graph there. We're told that the supply voltage is 12 volts, and we're asked to calculate the resistance of the thermistor. Well, in order to do that, we're going to use our relationship between V, I, and R, because we know V, we know I, and we need to know R. This is where we're going to use our equation. I'm writing this in multiple form, V equal to IR. Voltage is real, that's the way I like to remember it. Okay, voltage is real. Now obviously we know V, we know I, but we don't know R. So what we can do then is simply put in our numbers. We can rearrange and then we can write in the answer. Now you may have done the rearrangement earlier, you may be happy saying R is V over I. However, some students are not happy, and so this would be perfectly suitable for our Cambridge examinations, simply to rearrange after you put the numbers in. There's no shame in doing that. So we get a resistance of 92.3. Now notice here, this is a 3-mark question. Sorry, you can't see it on the screen actually. This is a 3-mark question, believe me. And one of those marks is for the units. So make sure you include your unit there of resistance. Okay, and that's even if you cannot write the answer to the question. Okay, that is even if you found that calculation too difficult, you always get a mark simply for stating the units of resistance. Now so far it's been a fairly straightforward question about resistance calculations. However, we now get to the point where we think about using the graph to describe what happens to the current and then the resistance in the thermistor. And that's what's really important here. So we're looking here, use the graph to describe what happens to the current. Let's literally read what you can see. Well, as the temperature increases, the current in the thermistor also increases. So we can see there that we've got a larger current for a larger temperature. The key bit here now becomes we go from describing, up in the top question here, to explaining. And this is a really great kind of jump there. It's only a 1-mark question, but it's worth us thinking about it. How does the figure, the graph, explain the relationship between resistance and temperature? Well, if we notice here, as we've said in the first part of this question, the temperature increases, the current will also increase. Well, why does it increase? Well, if you think about it, resistance is opposition to current. So the larger that current, the lower the resistance. The higher the current, the lower the resistance. And therefore, as temperature increases, resistance decreases. If we think back to our original graph that we saw on the first page, you will remember that as temperature went up, resistance went down. Okay, and that's exactly what's being shown here. So even though we're looking at it from a slightly different viewpoint, actually the graph shows us that the resistance is going down because the temperature is going up. So quite a nice little question there. Not too much about the thermistor, you're not expected to know how it works, but you are expected to know how the current will behave, the resistance will behave as we change the temperature, and you may be asked to do so for an LDR as well. Alright, if you've got any more questions about LDRs and thermistors, please let me know. I hope that was of help. And if you've got any other concepts you'd like me to explain, please feel free to message me and I'll put something together as and when I can. Thank you for watching and all the best for your preparation for your examinations.